All right. Welcome. Chapter 9. New chapter here on trigonometric ratios and functions. Um, a lot of new stuff, I think, coming at us here. Probably something that, different than a lot of chapters we do where you've been exposed to a lot of stuff. We maybe get into some details further details as far as expanding on previous concepts. I think chapter 9 is a little bit different in that most of the stuff coming at us is pretty new. We're still going to use some skills. We're going to simplest radical form fractions involving square roots and uh, using proportions that we maybe to solve equations and stuff like that. So we're still going to use skills, but I think a lot of what is covered in the chapter is going to be new for us. So make sure you're asking questions, you're staying on top of um, homework and all that. So let's jump in. We'll focus today. I know sometimes I'll go through with you to kind of just see some of the different stuff. We'll finish with some graphing. We'll talk about radians and this unit circle. Today, mainly focus on this first goal, trigonometric functions and right triangles. So let's talk about it. So today's specific lesson, we'll actually break this up into two parts to keep the videos manageable. That's how we'll do it in class as well. I think there's probably a little bit more than we can cover in a single class period. So we'll break the notes that way too, or the video notes that way as well. So I've got a spot we're going to get to, and then we'll have like a part 2 to follow. So right triangle trig, maybe you've seen this before. This would be the one thing that probably or it would have maybe come up in a geometry class. There's a lot of geometry here that we'll do. At least portions of this will involve quite a bit of geometry concepts. Sine, cosine, tangent are probably if you've heard of some of the stuff, those might be functions you've seen, or you've maybe even seen them on your calculator. So that's what we're going on. I know lots of stuff to cover. We'll get through probably these 1.5 here for the first note. So I think it's a good spot. That's why we're breaking it. So here we go. Let's jump in. No more talk. Well, obviously plenty more talk, but no more build up. Let's do it. So first note section you should have is what's called parts of a right triangle. Definitely we should all be familiar with at this point the hypotenuse. Right, that's the long side opposite the right angle. There's a little symbol going on here called theta. It's a Greek letter, theta, Theta. It's almost exclusively used in math as far as specifically trigonometry to represent an unknown acute angle in a right triangle. And I guess I wouldn't necessarily always have to be a right triangle, but just an unknown angle. A lot of times we'll mainly see it as an acute angle, but it's essentially an x. It's an unknown angle measure. Okay. The other two, this is such a huge deal on the first slide of the notes. First slide, first lesson. These other two terms, opposite and adjacent side, I know you're probably used to calling, well, there's the hypotenuse and the legs, right? So these would both be legs, which they still are. They're still called legs, but we're gonna want to converse and talk about the opposite and adjacent sides. That can change. So it's all perspective. If we're standing here, or let's just say that this is called the opposite side based on theta being right here. Okay, so if I were to walk out from my little spot, what side is opposite of me? It's not the side next to me. It's not the hypotenuse. Is always called the hypotenuse. The side right next to me, which is down here, would be my adjacent side, the side that I'd have to kind of walk, that I'm not touching, it would be my opposite side. Okay, the one right next to me is adjacent. But that same picture, my hypotenuse is still up here. But if my theta now is all of a sudden up here, what's changed? Well, walking out from your theta, now your opposite is down here, and your adjacent is right here, right next to you. So sometimes students struggle with that the entire chapter, wrapping their head around that. Well, I thought it was always this side. I thought it was always that side. It's all like perspective on the angle that you're using or the angle in question. So that's how we come up with those terms. Okay, so that's some of the terminology that we'll use. All right, let's get into these trig functions and what we're talking about here. I mentioned sine, cosine, tangent earlier. So the first thing, what the heck is a trigonometric function? Again, add this to our notes. This is kind of the why. Like, why are we able to use trigonometry? I know it's like this big, scary math class that you hear about in movies. They talk about trigonometry. What is it? This is kind of the premise behind it, that especially with right triangle trig, that every acute angle measure in a right triangle has its own set or its own unique set of ratios of side lengths. So for example, and we did this in class where let's say I've got a right triangle right here, and there's a 42-degree angle. I know I'm kind of writing small. It says 42. And then I've got a totally separate, larger, these aren't meant to be the same, but I've also got a triangle here that has a 42-degree angle in it. What I'm telling you is that if I take this side, and it doesn't matter, this side right here, and I say, you know what, for whatever reason, I want to divide x by y, that's a ratio. So that's what we were talking about right here, ratio. If I take x divided by y, I'm going to get some number, right? Assuming these are all numbers. X divided by y is whatever, it's a. The kind of the cool part, as long as I'm following the same order and saying, all right, I've got a side over here. This can be side P and side Q. Now I'm trying not to screw this up. I'm looking because I'm using the opposite side of 42 and then the hypotenuse in terms of this 42. I want to make sure I have the opposite side and the hypotenuse. So if I did that same thing and said, you know what, just for the heck of it, I want to divide P by Q, I should and I would get the exact same number. A is over here, even though these, X and Y are going to be completely different lengths, right? This is, I get my ruler out and say, hey, that's 1.2 inches. This is 3.4 inches. I measure over here. This is 4.8 inches. This is 9.6 inches. When I divide them, I should be getting the same number. So that's kind of what's at play. That's what's behind trigonometry, at least right triangle trigonometry, is that, and I just picked 42, for example, as like an example. But 42 has its own unique set of side length ratios. Okay, so that's kind of what's going on there. So hopefully you follow a little bit of that. All right. There's 6 trig functions that we're responsible for knowing. Okay, so this part is all about just kind of knowing the different ways we can arrange side lengths, basically. Okay. So we pretty much took this note in class. So if you need to, obviously pause it here, add this section to your notes. You could use we used a picture. You can almost use the exact same one that we had before with theta, right triangle. In terms of theta, right, this would be my opposite. This would be my hypotenuse. This would be my adjacent. Okay, so it's nice to have a little picture, but these are the 6 trig functions that we're responsible for knowing. So, and these are all abbreviations too. This little sin, cos, those are the buttons that you would have probably seen on your calculator. Tan, they stand for, there's actual words there, like sine, S-I-N-E. That's what sin stands for, sine. Cos stands for cosine. And tan stands for tangent. Okay. So let's start with those ones, I guess, just for right now. There's a lot thrown at you. I know if you're right, and you can obviously pause. The sine of an unknown, of an acute angle is equal to, in any triangle, no matter what the angle measure, in a right triangle is equal to whatever the opposite side length is, divided by or over, like in a fraction, as a ratio, over the hypotenuse length. That's one way you could arrange these letters, right? O over H. Another way you could arrange them would be to take the A, the adjacent side length, and put it over the H, over the hypotenuse. A third way you could arrange these letters would be to take the O and put it over the A. So that's what tangent is. So it's really just a matter of, there's a kind of a fancy name, sine, cosine, tangent, for ways to arrange side lengths, is really all it is. Now, it's a lot to remember. So what we're going to use, and this might be something you've heard, maybe not. If you don't know it, it's something we're going to use so much that I think just out of like necessity, you'll have to memorize it or remember or whatever you want to, however you want to say it. But it's kind of a nonsense phrase. So katoa, right? So that's kind of a famous math phrase. You might ask somebody that's taking, oh yeah, I've heard of SOHCAHTOA. A lot of times when people just see that or hear trigonometry, that's the first thing they think of is, oh, SOHCAHTOA. Yeah, I know what that is. So let's make sure we understand what this is here. The S stands for sine. The C stands for cosine. The T stands for tangent. And if I can remember the phrase, I can remember how things go. Look at sine is equal to opposite length over hypotenuse length, right? Right here and here. Cosine is equal to adjacent length over hypotenuse length, right here. Tangent is equal to opposite length over adjacent length. So it's kind of a little just trick to remember like how these all go, which we do, like I said, third or fourth time now, we do have to know sine, cosine, tangent, how are things arranged. So up to, if we can get those down, hopefully we can get those down. There's three other ones, but you see it right here, they're reciprocals of these ones. Okay, so it's not like a whole new set. These are just three different ways you could arrange these. So, if I were just, what does this CSC stand for? This stands for cosecant. Cosecant. The secant then stands for secant. And the cot stands for cotangent. And if you look, I could still get by, I think, using the SOHCAHTOA. So for cosecant, it's hypotenuse over opposite instead of opposite over hypotenuse. Same thing here. Secant is going to be, instead of adjacent over hypotenuse, it's hypotenuse over adjacent, and then cotangent, adjacent over opposite. So I think what these three hinge on is knowing who's the partner. Like sine and cosecant are partners. If I know sine, I know cosecant. Cosine and secant are partners. If I know cosine, I just flip it over and there's my secant. The one that's probably the easiest to remember is tangent and cotangent because obviously they sound the same. Here's what I do. I can give you the Mr. Kroll spin on it. You would think, right? It makes so much sense for cosecant to go with cosine, right? Doesn't that just make so much just common sense? Cosecant, cosine, and sine to go with secant, right? Doesn't that make so much sense? Yeah, well, that's not how it goes. So I'm like being honest, like that's how I remember it, the way that I think it should go, co and co. Yeah, that's not how it goes. Okay, so come up with something that you're able to remember. Hey, sine always goes with cosecant, and cosine always goes with secant. Like I said, tangent, cotangent, that one's easy because they sound the same. But so figure that out as far as how you're going to keep that straight. And then the last part, it's not anything new, but depending on what we know, just it really kind of hinges on this idea of kind of an old concept of what is a reciprocal. It's flipping something over, right? We said, hey, kind of flipping a fraction is the reciprocal. But like mathematically, how do you flip something over? If I want to flip 2 over, I say, oh, I got to divide that by 1. And that becomes 1 over 2. If I want to flip 2/3 over, and I know you don't really ever see it like that, 1 divided by 2/3 is 1.5 or 3 over 2. So that's how you like mathematically would flip a fraction. I know I'm using the word flip kind of loosely there, but I think we understand what that means. That's how you mathematically flip a fraction. So that's why we're saying there's different ways to maybe see it. The cosecant is equal to the sine flipped over, 1 divided by the sine. So like, let's say I knew my sine was 0.1, just as like a mini example right here. The sine of some angle equals 0.1. What is the cosecant of that? Well, the cosecant would be, let me grab my calculator here. Well, I should be able to do it without a calculator. 1 divided by 0.1 is 10. So the cosecant of that angle is 10. So it's really it's a different way to kind of see, or or to think about those other three, the cosecant, secant, cotangent. We'll just kind of as it comes up, but I would still add it to my notes. Cosecant, secant, cotangent are 1 over cosine, 1 over tangent, 1 over sine of theta. So kind of a longer page of notes there, but definitely worth having. Like that's something we should have in our notes. Okay. So I've got 2 examples here, and then we'll hit one more concept, an example, and then we'll break there after this one. So I know that's kind of a long deal there, but we're doing okay. It's not the end of the world. So just really all this is recognizing, how are these things situated? So I see the question, obviously sketch the picture, get it set up, and you can wait, we can do it together or give it a shot. So what is it asking us to do? It says evaluate the 6 trigonometric functions of angle theta. All right. So, what is this question even asking? Sometimes people see that and they're like, what? Evaluate the 6? Evaluate them? What are the 6? So it comes, initially it's, all right, I want to know, or the question's asking, what is the sine of theta? What is the cosine of theta? What is the tangent of theta? Right? These are, when I hear that phrase 6 trig functions, that's what it's asking about. I'm trying to group them in a way that makes sense to me. Sine, cosine, tangent, those are kind of the big 3. And then which ones, what do we call the reciprocals? Oh, here we go. Is my first test. Sine, that's the one that goes with the co. So cosecant of theta. The secant then, right? I'm flipping it and thinking kind of counterintuitively. And then cotangent. So that's what the question's asking in the end. What are the 6 trig functions of this theta? The other thing that I think for sure I need here is that phrase. I'll maybe put it over here. So, ka, toa, because that's almost like my cheat sheet. That tells me how things should go, how things should be situated. So, we're almost there. I think I can almost kind of start going. So this is all just set up. All right, that's what I'm asking for. This is going to help me, the SOHCAHTOA. The last thing I need to see all the side lengths. I don't know why this says hypotenuse. It's like a weird, just hanging out there. It's bothering me. So can I get rid of it? Kind of. Not nearly as good as I hoped I was going to be able to get rid of it. But anyways. Stuff that I think I still should be kind of doing to set up here, because everything's written in terms of opposite, hypotenuse, adjacent, hypotenuse, opposite, adjacent. I think something that's easy to do is, put your little person, or however you want to keep track of it, standing at the theta, label your sides as H. Okay, the side's always H. This side over here would be my opposite. This side down here would be my adjacent. So that's an easy thing to do on any problem that involves a right triangle, is label your sides. And then I think the last part, before I kind of start answering questions here, I want to find that H. What the heck is H? This is old school. We haven't done this year, but it's something that gets covered, I think, in depth. It should have gotten covered in depth in a geometry class or a previous math class. We're going to use our Pythagorean theorem. Oh, yeah, going old school there. In a right triangle, only can be used in a right triangle. But if I square the both legs and add them together, I get would be equal to the hypotenuse squared. So leg squared plus leg squared equals hypotenuse squared. So for what the information that we have, I'd have to take the 8 squared plus the 15 squared, and that should be equal to c squared. So I think when I do this, 64 plus 225, I get 289. I'm just getting low on the screen here, so I'm trying to shortcut it a little bit, but I just did 8 squared plus 15 squared, and then the square root, I need to undo that squared. The square root of 289 is a nice number. C equals 17. Just know this isn't always going to be a nice number. So we'll see. I think the next example involves one that's maybe not such a nice, not that it changes really anything that we would do, but just be aware that you're not making a mistake if it works out to the square root of 50 or the square root of 20 or anything like that, okay? All right. That was the information we needed. That was kind of the missing piece of the puzzle, because now I'm just running through my SOHCAHTOA. I mean, you can use your cheat, you can use your notes, but I think this, like I said before, this is my cheat sheet. This is all I need to see to answer all 6 of these questions. What is the sine ratio here? All right, I got to go to my cheat sheet. Sine is equal to the opposite length, which is 8, over the hypotenuse length, which that's why we did that work to figure out that, oh, it's 17. So whatever this angle is, right, it's got its own unique ratio. It's got an 8/17 sine ratio. What's its cosine ratio? The adjacent length, so right here, I've labeled it already, is 15, over the hypotenuse length is 17. And then tangent ratio is equal to the opposite length, 8, over adjacent length, 15. And if I'm confident in all these, which I think I am, I should feel decent about them. I followed my kind of guide here, SOHCAHTOA, and I can remember, hey, you know what? Whose partner's who? They're all in the right spots. All I need to do is literally flip every one of these over to say, okay, it has a cosecant ratio of 17/8, secant ratio of 17/15, and a cotangent ratio of 15/8. We can leave them like that. If these did reduce, obviously having a 17 in there, a prime number, nothing's going to reduce involving a 17. But if this was like 8/16, obviously I would want you to reduce that to 1/2 or 2/4 or whatever, So reduce fractions whenever possible. But that's it. Like that's your answer for this one. So it's kind of a weird looking, like, oh, all 6 of those. Like that's what that's asking for. All right. Let's do the next one. I call it checkpoint 1. You could call it example 2. It is a different example. It's not the same question, and it's you can see there's no picture or anything like that. So let's take a look. Again, pause, get some of the information. I think the big thing is, theta is an acute angle in a right triangle. Okay, that's kind of how we defined it. It's telling us, it's given us one of my ratios. It tells me, hey, the cosine of theta is 3/8. Find the value of the other 5 trig functions. So it kind of the same question in that, what is this asking about? It's asking for the sine of theta, the cosine of theta, the tangent of theta, all right, here we go again. Can I do this? The cosecant of theta, the secant of theta, and the cotangent of theta. Wait a minute, hold on, Mr. Crow, you're lying. It's not asking for all 6. It's only asking for 5, right? Because it actually gave us like a freebie. Hey, this has got to be, it tells us the cosine of theta is 3/8. So indirectly, that one was free. It almost gives us, as long as you know how this works, that, oh yeah, this has got to be 8/3. Not bad. Like, I'll take that, right? That's not a bad free, almost free second answer there. So this kind of boils down to, all right, what is sine, cosecant, tangent? If I can figure out sine, I'll flip it. If I can figure out tangent, I'll flip it. So here's what I would do. I feel like we're missing numbers, right? So it's almost like I want to make that same, I'm trying to think how that last one was situated. I almost want to make a picture where I have a theta. I label my sides, right? This would have to be opposite of theta. I wish I could make it. I know what's going to happen here, so I'm trying to avoid using this space on the right. Let's see, can we clear? Let's try. Bear with me for a second. I'm just trying to get a little space. I think. Oh no. Hopefully we got the information. I just want some space to work without having to write down here, because I know there's going to be a simplified thing that I want to make sure I have room to do. So let's try this again. What I want to finish this problem is a picture. Right triangle. I can use the same almost generic picture that I had in the last one. What was one of the things we did? We labeled the sides. Oh, this would be my opposite side. This would be my hypotenuse. This would be my adjacent side. I think at some point, whether it's now, whenever, I need to put, or I want to see that same phrase, SOHCAHTOA. So that's going to come up at some point. And then I think the last thing we need is, well, I need numbers here, right? So this is telling me kind of where this 3 and this 8 go, right? Because cosine is equal to the adjacent length over the hypotenuse length. So the adjacent length has got to be 3, right? Because I took it and I put it over 8. So 8 must have been the hypotenuse length. And at this point, we're basically right where we were when we started that last problem. Actually, we're a little bit further ahead because we have 2 of these done. So here we go. Let's do the Pythagorean theorem. I got to figure out what this opposite side is. Different, setup on the Pythagorean theorem, though. It's going to be 3 squared plus, let's just call it x squared. That's what we're looking for. This side over here has got to equal 8 squared. So 8 squared is 64. 64 minus 9. I'm just trying to save some space. So x squared equals 55. We would square root both sides. So it's a good look that, okay, this is the square root of 55. It's not perfect. It's not clean. I don't want decimal answers there. Let's try to stay as exact as possible. The square root of 55, that's fine. If I could pull out a perfect square and, simplest radical form this, I would do it, but there's nothing that goes in there. So I think we're okay. All right, from here, let's roll. Let's go through our process. We should hopefully be getting a little more comfortable with this. All right, go to my SOHCAHTOA. Sine, right? That's the first one we got to answer. Sine of an angle is equal to the opposite length, which we just found, over the hypotenuse length, which we already knew, or we kind of got on the triangle where it went. Let's do tangent right away. Tangent is equal to the opposite length, square root of 55, the one that we just found, over the adjacent length, which we know is 3. What makes this one even just a little bit, one additional piece, is when I go to flip these, because that's not changing. I'm going to flip the 8. So the reciprocal here for cosecant is going to be 8 square root of 55. And then, whoops, I wrote this one all goofy. The cotangent of theta is equal to 3 over the square root of 55. And that's not wrong. Just think back, though. What did we say? When writing a fraction, one of the rules for simplest radical form is we never want to have a square root in the denominator of a fraction. Yeah, so it's a simplification thing. So just hopefully we remember that. How do I fix this? Remember, we want to multiply both the numerator and the denominator by the same thing, and will be simplified. Okay, so the 8 times the square root of 55 is just that, 8 times the square root of 55. Don't multiply those numbers. And then the square root of 55 times the square root of 55 is just 55. And then I get kind of that same thing going on down here. 3 root 55 over 55. Still, I would look to reduce anything that I can. So just, again, as a review on some of that stuff, I can't reduce this 55 and this 55 just because one's in a radical and one's not. But if this 8 happened to simplify with the 55, I would reduce that fraction. Like if this was 8/56, 8 goes into 56 7 times, so I'd 1/7. But just, again, they don't reduce. I just want to make sure you know that, hey, I would like you to reduce these whenever possible. All right. So that's kind of the first 2 involving that concept. 2 types of questions. Just really checking to see, do we know these ratios? Look at all those notes on there. Do we know these ratios? Do we know how things should be situated? Okay. The last concept for this notes session would be these. I'm actually going to go off the grid here a little bit, and let's call it let's just call it special right triangles. Okay, so this would definitely have been something that came up in geometry. Excuse me. So there's 2 that we got to know. What makes them special? It's their angle measures. So the first one is what's called a 45-45-90, right? Why is that special? Well, it's half a 90. So it's this isosceles 45-45-90 triangle. Obviously, you can see that, like even construction, architecture, the 45-degree angles are a common angle that come up. And then along those same lines, different angle measures, but a 30, 60, 90 triangle. So those are the 2 what we call special right triangles. And what I'm asking you to know about these ones is, just because they're so common, because we see them a lot, these are the only two triangles or the only three angles that I'm going to ask you to know their side length ratios. So here they are. That part's easy. 30, 60, 90, 45, 45, 90. It's knowing where these side lengths kind of fit in. So let me put them on here, add them to your notes, and then let's talk about them just for a second. So in every 45, 45, 90 triangle, I'm not saying that there's a 1 inch and a 1 inch side, but I am saying that there's a 1-to-1 ratio on side lengths on the sides opposite the 45. So in other words, that's why I said earlier that this is isosceles. If this is 50, this is 50. If this is 20, this is 20. All right, that's just an example. The hypotenuse is always going to be the square root of 2 times bigger than this side. So if this is 4, this is 4 times the square root of 2. If this is 10, this is 10 times the square root of 2. That one's harder to wrap our head around a little bit. Let's look at the 30, 60, 90 just to kind of illustrate. So in every 30, 60, 90 triangle, the hypotenuse will always be 2 times bigger than this side. So it still applies. If this is 1, this is 2. If this is 50, this is 100, that type of thing, okay? So one thing, I don't have an example set up for it, but one thing I might ask you is, just as a kind of like a mini example, what is the, or find, let's just say it like this, find the exact, let me think here, tangent of 45 degrees. Exact, not a decimal. What is the exact tangent of 45 degrees? So it's the kind of, I think, the third example in a row where I want to set up my SOHCAHTOA. And I don't know if I need the whole thing because this one's only asking about tangent. So basically, what is the tangent of 45 degrees? Well, I know this. The tangent, right, we're used to writing theta right here, but I'm replacing theta with 45 because it's not unknown anymore, right? I know that, hey, the unknown, it's not unknown. I'm misspeaking here. The tangent of 45 is equal to, what's tangent again? It's the opposite side length over the adjacent side length. And I know you're like, well, are these side lengths? They kind of are. Like, it's just kind of as simplified as you could get. They're like reduced side lengths. The tangent of 45 is equal to the opposite length. So let's put ourselves at either one. It's not going to matter, but let's put our little guy or our little person, our little theta. Again, theta is probably not the right thing to use, but we're standing there. I can still label all my stuff. Like, this would be my opposite side. This would be my adjacent side. This would be my hypotenuse. So when this is saying, hey, tangent, take the opposite side length. All right, I can do that. Opposite is 1. And put it over the adjacent side length. Oh, the adjacent's 1. Cool. The tangent of 45 is 1. Exactly 1. So that one's kind of nice. It simplifies nice. Obviously, we could see things if the same question said something along the lines of what is the sine of 45, then I would have to be taking, let's see, I'll just do it, write it out quick. The sine would be the opposite length. All right, opposite is still 1 over the hypotenuse. Oh no, square root of 2. So it's one of those ones that, like we just saw, where I'd ask you to simplify that and say, hey, the exact sine of 45 degrees is equal to the square root of 2 over 2. Right? So I just simplified this one right here. So obviously, it could ask you any of those, hey, find the cosecant of 30 degrees, find the cotangent of 60 degrees. All right. I would never ask you the cotangent, at least for right now. What is the cotangent of 90 degrees, or what is the secant of 90? Right now, we're only ever going to stand at the acute angles. Okay. So you can see here, this is why I skipped over this. I didn't want to, I'm not, by no means am I saying you better memorize this. That would be just dumb of me. That's not what we're in the business of doing. I'm looking to understand the concepts that, hey, there's two kind of big right triangles here, or two kind of special right triangles. All you need to know to answer any one of these questions, doing kind of what we just did was, where did it go? Oh, right here. Using your SOHCAHTOA along with those side length ratios. Okay, so I am asking you to learn, memorize, know, whatever you want to say, that, hey, in a 30, 60, 90, there's always a 1 opposite the 30, there's always a 2 opposite the 90, and there's always a square root of 3 opposite the 60. I always draw it this way just so I can go 1, 2, 3. Just don't forget to put the square root here. Same thing here. There's always a 1 opposite the 45s, and then the hypotenuse is square root of 2. All right. The last thing that goes along with this is we'll kind of start to get into, and that's more into the next section, of using those models to help us find unknown side lengths in these triangles. I'm going to give myself a little bit of room here. I think we'll have enough. I just want a little bit of room I want to be able to see these two again. So I'm going to put my 45, 45, 90 with its side length ratios, and my 30, 60, 90. All right, and this way too, and the other advantage of me kind of always drawing them the same way is I always have the square root on the quote unquote bottom. So it's one less, it's just, I don't know, in my head it makes sense. Maybe you got your own way of keeping them track, but I do need you to know where these side lengths go. 30 would be here, 60 would be here, and these are both 45s. So how do I use them? How would I answer a question like this? Find the exact value of x here. So the only reason I can do this is because it's got a 30 degree. It's like, oh, I know what how these should line up. Like if I take this 8 and divide it by that x, on this triangle, the hypotenuse over this adjacent side, if I take the 8 and divide it by that x, so just hear me on this first one, let's talk about it. The hypotenuse divided by adjacent for 30 degrees needs to be the same as the hypotenuse divided by adjacent for 30 degrees. So this 8 divided by this x has to have the exact same value as us dividing 2 by the square root of 3. So it's not, the square root of 3 scares people. It's, I don't like that square root of 3 in there. But that's what the ratio is, right? We're going back to the very beginning when we said I don't need to click to it, but each acute angle has its own unique ratio. Well, a 30-degree ratio is 2 over the square root of 3 when I start talking about the hypotenuse and the adjacent side. So what we've created basically is a proportion. How do I solve that? Anybody remember? I would say there's different ways that you may have seen. I think the easiest way to do it is to cross multiply. That's something I think most students are familiar with. So to solve this, the cross products basically have to be equal. So 2 times x, that's an easy one, 2x. And then 8 times the square root of 3. Okay, 8 times the square root of 3 is 8 times the square root of 3. And then, solve for x. Sometimes the x will just end up by itself. In this case, it didn't. So what do I have to do to get the x by itself? Divide both sides by 2 to get x equals, and here's a good look at, I can reduce that. What's 8 divided by 2? 4. So 4 is in the numerator. 4 times the square root of 3 is what we would end up with for that value of x there. There's different ways. Like I said, some people say, you know what? Hey, if this is 8, doesn't this have to be 4? And that's totally true. And doesn't this down here have to be the square root of 3 times bigger than this side? And say, yeah, that's actually right. So there's different ways you can kind of get there. I'm going to follow that same process. I think over the years, most students have had success with using the proportions. So I look here. I'm going to set the exact same setup. I just need to be working with a different triangle, right? This is a 45, 45, 90 triangle. So I need to work with a 45, 45, 90. So it's the same deal. I'm going to set up the same way. If I take this x and divide it by this 6, right? I'm taking one of the legs and dividing it by the hypotenuse of a 45, 45, 90. I need to get the exact same thing as if I take this leg and divide it by this hypotenuse, right? So if I take 1 and divide it by the square root of 2, that needs to be the same as x divided by 6. Why? Because they're similar right triangles. This one I think it simplifies, maybe a little bit tougher, so that's why I'm solving it this way. This first one's kind of not so nice, right? X times the square root of 2 it's not terrible. It's x times the square root of 2. And then this one's nice. 6 times 1 is 6. But I know a lot of students get here and they're like, I don't know what to do. Do I just move this over? And you say, no. Like, this is just, how would you get rid of a number that's being multiplied by a variable in a one-step equation? You'd say, I need to divide both sides by the square root of 2, right? This is just a number. You divide by it, right? So that I get my cancellation going on. And I say x equals 6 over the square root of 2. And you're like, oh, dang it, that's the third time I think today that this has come up. Let's fix it. All right, so hopefully at this point you're like, yeah, I know how to fix that. I can't leave that 2 downstairs, that square root of 2. So I get 6 square root of 2 over 2. And then this 6 and this 3, they're both outside a radical, so we could reduce them and say, whoops, that's a 2 there. Sorry, I was doing some reducing in my head. And I was writing what I wanted to write on this next step. 6 divided by 2 is going to be 3. 3 times the square root of 2. So sorry if I lost you there on that last step. That should have been a 2. I miswrote it. So yeah, I don't know. It kind of varies. That's not super easy. I don't think anything we've done today is super easy. So obviously, make sure you're finding a little bit of time to add these to your notes. You're not going to get it by just watching me do problems. So make sure you add these to your notes. We're going to break there. It's a good spot. That's where we stop in class. So I'm going to leave it at that and say we've definitely evaluated trig functions. Like, we've found them all. We've found unknown side lengths, right? We just found 2 of them. They were not like super nice numbers, 3 times the square root of 2 and whatever the other one was. But we've only done it for special right triangles. So we still have a little, I'd say we've done like half of that. All right, what about like a 32-degree angle? What about a 51-degree angle? We got to cover that next, okay? So we'll break it there. This will be part 1. Stay tuned for part 2 or catch it on the next lesson. So that's it. That's all I got. I'll see you in the next lesson.